If I'll talk in the next, however many minutes about at least two of these, and then see how far we get with that. I want to make sure that we fully understand how to graph these transformations, okay? And then at the end of the period, I want to talk about a situation that occurs with some of these, okay? Or I guess it occurs with all of them, but we're only going to address it with some of them. So what I want to do is I want to take the time to graph this. What does that number right there do to this? Actually, before we do anything, let's write this way. If I had plus or minus a sine or cosine of like bx plus c plus d, we don't like graphing that. That is difficult to graph. So what we do is we actually pull that b out of the argument, and it leaves our x coefficient to be 1. We have to make things just so much simpler for ourselves, we have to have our x coefficient to be 1, okay? And then that c value there is actually c divided by b, because we had to factor the b out of that quantity, so you factor out of both terms. Once you have your equation written that way, okay, once you have your equation written that way, you can then begin the graphing process, okay? So right now, we don't have ours written that way. So what I want to do is I want to factor that 3 out of the argument, okay? Because that 3 needs to be a 1, right? So I factor it out. So it's going to turn into y equals -3 cosine. Okay, then I'm going to put a 3 there, and now it's going to be, so when I factor the 3 out of 3x, it leaves me with x. And when I factor a 3 out of essentially 1/2, okay, it leaves me with what? 1/6. Okay, so it's going to leave me -pi/6. The way I do that, when you factor out, you're dividing, right? But when I divide by a whole number, that's the same as multiplying by, but what fraction? The reciprocal, okay? So instead of actually taking pi/2 and divide it by 3, I just took pi/2 and multiply it by 1/3. I think that's easier, especially when, and we're not going to see one today, but that 3 that we pulled out could have been a fraction. It could have been like 2/3 that we divide out. If I have to divide out 1/2 by 2/3, then I multiply by reciprocals to do that. So it just makes sense to just, every time that you factor out that 3, or whatever that b value is, just multiply by essentially 1/b, and it'll make things a little bit easier for you to see what your argument should be. But when I'm done doing this, I just quickly just redistribute that in my head and make sure I get back to 3x minus pi/2. Okay? I want to make sure that I adjusted this correctly, because if this is wrong, then my graph will not be that, right? Does that make sense? Okay. Sometimes they start you off this way, and you don't have to do anything. Okay. But if your x coefficient is not a 1, you have to address that. So now, what does that -3 right there? There's two things that -3 does. What is one of them? Stretch. Which direction? Vertical. And then reflect x-axis. Those two I'm going to do together eventually when it's not hard to stretch and reflect at the same time. What's this pi/6 do? Right? Pi/6 units. Okay? Which that tells me right there how I need to set up my x-axis. Okay? I must make sure that when I'm done, as we develop our x and y axes here, that my x-axis is in terms of pi/6. It will make moving things so much easier. Okay? And in this one, I believe that will kind of take care of itself automatically, but it doesn't always do that. We always want to pay attention to our x-axis units. And then this 3, okay, that 3 is actually going to be a horizontal compression, okay, which is going to ultimately be determined by our period. And our period is always 2 pi divided by b, And that 3 right now is our b. So the period is 2 pi over 3. And because of what our period is here, because of our period being 2 pi over 3, that is a multiple of pi over 6. So when we work through this process of scaling our x-axis, our pi over 6 will show up, and that will write our x-axis in terms of pi over 6, which will be nice for us. Is that okay? So those are the things that are going to take place. Now what we do is we set up our x-axis. Okay, we have to be able to do this on like tests and quizzes. I will probably most likely just give you that spot right there, and I'll tell you that's where I want one period to kind of be started. Okay, or I guess finished. Start here at 0, and then this will be out to, that'll be our period, 2 pi over 3. So the whole graph is going to oscillate one complete time in that distance. Does that make sense? Okay. The next thing we're going to do is we're going to start cutting this thing up in halves. If I cut that in half, what is half of 2 pi over 3? Isn't it 1 pi over 3? Okay. So just multiply this by half. Multiply by half, you get the 2's cancel out, and you're left with pi over 3. What if I cut this distance of 0 to pi over 3 in half? What do I get here? Pi over 6. Take pi over 3 and multiply it by half, right? And ultimately, guys, what I'm doing here with this pi over 6, I'm trying to find the midpoint of that interval right there. Okay? And because once I find that midpoint of that interval, I create what is going to be our smallest distance that we use to kind of move ourselves along the x-axis. Okay? So that pi over 6 is going to be kind of our, maybe we call it an index, to where it's what we use to kind of count or determine our position. So there would be 2 pi over 6's, right? What would this one be? How many pi over 6's have I used to get to right here? 3 pi over 6's, right? So I'm going to rewrite that as pi over 2. So you can see then that this thing structures our x-axis correctly. So then that would be 4 pi over 6's, right? And then this would be 5 pi over 6. You can go one more if you want to, and get to pi. Or you can go one this way, and I get to negative pi over 6. Okay? And per this one, we at least need to, you'll see here in a little bit, we at least need to get to that 5 pi over 6 x value because we got to shift to the right, and that will then put that 2 pi over 3 point at 5 pi over 6 eventually. Okay? So that's how we construct our x-axis. Okay? Just taking halves of things all the way down until we get that an initial distance, and then using that and basically counting then to set up the rest of the x-axis. And that, if you think about what we did with the unit circle here when we started counting around, we went, what do we call that? We said 1 pi over 6, 2 pi over 6's, 3 pi over 6's, 4 pi over 6's, 5 pi over 6's, 6 pi over 6's, 7 pi, 8 pi over 6's, 9 pi over 6's, 10 pi over 6's, 11 pi over 6's, 12 pi over 6's, right? That's what we did when we're trying to create the radians. Okay? It's essentially the same thing. When we did this on the unit circle, we had to figure out what was that initial arc length, and then we just kept replicating it, right? Well, here, we have to find that initial distance, and then just keep replicating it over and over, keep adding it to itself to move across the x-axis. My y-axis needs to be between 3 and negative 3. Because that's what this amplitude here is telling me, right? That's that number out in front. Okay. Now what I'm going to do, and I think this is important, this is the purpose of what I gave you today at the beginning. I asked you to graph y equals cosine of x. And that parent function is going to look like this. While you were taking the quiz, anybody notice that both of these were graphed on the board? Oh, you cheater. Huh? That's right. Okay. So we have that, right? And what I want you guys to realize is that there's a lot of symmetry here, right? Okay. Started there, ended there. Halfway in between, we get to our minimum, right? Halfway in between, essentially the y-axis and this dotted line here, we reach an x-intercept, and then the same thing over here, an x-intercept. So there's some symmetry upon that dotted line. We're going to use that same symmetry when we transform our graph here, okay? So when we transform our graph, the symmetry still exists, okay? We're going to squeeze this graph down. This is right now between 0 and 2 pi. We're going to squeeze that down to about, I guess, be about right there, okay? But when we do that, the relationships of how these points kind of order themselves with one another should still be the same. You cannot eliminate that relationship. Does that make sense? Through a transformation, okay? So what I mean by that is if I'm looking at the cosine, okay, the cosine between 0 and 2 pi over 3. Remember, this was our initial period for this transformation, right? Between those two things, okay? If we talk about the cosine, it should start at 1 and finish at 1. Does that make sense? And now all I'm showing you then right now is the cosine. So those 2 points come from this graph here, the cosine of 3x. That's all I'm graphing right now. Halfway in between, we get down to -1. And then halfway in between those points, we get there. Okay? So what I want you guys to see is this point right here, I'll call that point A for now, corresponds to the parent function at point A. Does that make sense? If I call this point B, that there corresponds to point B in terms of their position. Does that make sense? Okay. And that one I'll call point C, so that corresponds to there. And the fact that C was halfway between A and B in the parent function, then it has to be halfway between A and B down here in the transformed function. And then we got that point, and we'll call that one D and that one E. They correspond to those two. Does that kind of make sense? All right. So now here's my question. If that's cosine of 3x, that's what those points represent, what does the -3 out in front, what is that amplitude going to do to each of these y values? If it's a y value of 1, what do I do with it to address that -3? Yeah, you're going to flip it, and then it stretches, right? That makes sense, everybody? Or you can stretch it first, put it up to 3, and then flip it down. Okay? But say y value of 1, you multiply that by a -3, it's going to go to -3, right? Let's say y value of 0, what happens to it? We're going to multiply it by -3. Stays 0, right? This y value of -1, multiply it by -3, it becomes +3. Y value of 0 multiplied by -3 stays 0. And this y value at 1 multiplied by -3 comes down to -3. Is that all right with everybody? So right now what we have graphed, those points would be the points that come from y equals -3 cosine of 3x. Does that make sense? Now, what does the pi over 6 mean? The pi over 6 in our original transformation function, okay, original sinusoidal here, says minus pi over 6, right? So minus pi over 6 says you're going to take each one of these red points and you're going to shift it which direction? To the right, okay? So pi over 3, or sorry, not pi over 3, pi over 6 to the right would be there for that point. This one's going to go pi over 6 units that way. This one's going to go pi over 6 units that way. This one, pi over 6 units that way. And then this one, pi over 6 units that way. That reason right there, that shifting to the right, is why I wanted to make sure my x-axis was in terms of pi over 6, okay? Because then it's just moving, you know, in this case, just one interval, right? Okay? I think in the next one we'll see what to actually move 2 intervals. But regardless, it's easy to count how we move. If I had my x-axis labeled with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like we normally do with like polynomial functions, it's really hard to see how far pi over 6 is to the right, correct? If it was listed as like pi over 4, pi over 2, 3 pi over 4, that kind of stuff, it's going to be real hard to see how much pi over 6 is. But if we set our axes up that way, we can be exact with how we move those, okay? So now I'm going to connect those because those are indeed then the points for y equals -3 cosine of 3x minus pi over 2. That was the original function. Those are the points for it, okay? Now, usually what they ask you is they'll give you some domain to graph this thing across. They might say graph it from 0 to 2 pi, okay? Or 0 to pi or whatever. Well, if I wanted to do that, right now I'm not starting at 0, right? Okay? But we can use some symmetries. We can use the idea that if I know that point right there is a minimum, then it's going to have to go that direction, correct? Does this point right here essentially match to that? Or we can think maybe it's more specifically that one actually. But it allows me to find that. And we can see that our x-intercepts right now are pi over 3 units away from one another, right? So if I want to find more x-intercepts, I just add pi over 3 to each x-intercept that I have. There'd be another one. And I can keep playing that game. It's cut and pasting, essentially, as far as I need to the left and as far as I need to the right. Does that kind of make sense? Okay. I'm going to get on GeoGebra here real quick and just type the original function in because I think it's important to be able to check these graphically. Okay. So I'm going to give you guys a test on Friday. I'm thinking right now, and this is the way I want you to prepare, that the graphing aspect of these, I'm going to limit you by not being able to use Desmos and GeoGebra for the mere fact that you can essentially just type in the function and pull off points. Does that make sense? And that, in my opinion, doesn't display that you know what you're doing. So if I were to, for instance, I'll just use it real quick in Desmos here. If I go y equals, what do we say, -3 cosine of 3x minus pi over 2. Okay? But it was pi over 6 after I factored the 3 out, right? So if I do this now, when I click on the graph, obviously it puts these points in here, right? You see how it gives me those positions? That doesn't, so if I were to let you use this on a test, pretty much defeats what we're going through right now, right? And you just pull those points off, label your x-axis, and just copy exactly what you typed in. So I don't think that's displaying, what we want, okay? So I will restrict that in some manner, whether I fully take it away from you or I just ask questions where you don't fully graph something but target the concepts that I'm interested in, okay? That basically don't allow you to use your calculator. If you're on GeoGebra and you want to use GeoGebra, if you right-click on GeoGebra, go down to Graphics, and then you go to X-axis, you see where it says Distance. You can click on that, And you can, so if I click on 1, you see how it puts my x-axis in integers, right? If I click on pi, it'll put it in terms of pi. I go pi over 2. But what I like about it is I can actually go pi over 6. And then you can see the vertical bars. Each one of these vertical lines, see these gray minor axes or minor grid lines, is pi over 6 units. Does that make sense? Okay. So that's a nice thing about GeoGebra. Desmos doesn't do that. Desmos doesn't allow me to nicely change these x and y axes in terms of pi. This is GeoGebra. So we graphed like y equals, what was it, -3 cosine of 3x minus pi over 2. What I would do is I would just double check when I graph this by hand, does 0, 0 show up on this graph? And it does, right? Okay. Does pi over 3, comma 0 show up on this graph? Because that's the next order pair that we have here as an x-intercept. And pi over 3 right there. Does 2 pi over 3 as an x-intercept show up? Okay. And then here we'd have, what, pi over 3, 2 pi over 3, so that's going to be, 5 pi over 6 right here? Okay. No, that's not 5 pi over 6. No, it's pi over 2. Sorry, pi over 2. At pi over 2, do we reach a height of 3? So zoom in here, pi over 2, height of 3, I do. So I'm just double checking that my stuff I did by hand is validated through the actual graph that the calculator, the computer generates, right? So I know I'm right, okay? Now here's what I want you guys to kind of recognize. Do you think, let me just put the sine function in here real quick. The sine function on top of this, sine of x, okay? Let's make it red. What if I took that sine function and multiplied it by 3 out front? Okay, so I did that. Now let's do this. Let's take that sine function and multiply it by a negative. Okay, and now let's put a 3 right there. What did we just find out? Okay, so these two graphs are identical. Okay, so if I ask you to like graph x squared, there is one and only one way to graph that, right? There's only one algebraic rule that is used to show what x squared is. If I wanted you to write a rule for this curve, here's one rule you could use, obviously the purple one, but you could also use this red one. Okay? You could also use, let's go, -3 sine of 3x minus 2 pi. Does that one give me the same graph? Does that make sense? And the reason for that, folks, is that if I take, let's just make this A here, create a slider. I can move, so I can take that, so the red one is the same as the purple one here. The blue one is the one that I can adjust, okay? Do you see as I move it to the right that blue one eventually becomes the other ones, right? And then keep moving it to the right because of the periodic behavior, eventually it's going to become the red one again, right? So there's 3x minus 2 pi. I go 3x minus, let me get there, 4 pi, okay? So there's actually an infinite number of equations that produce the same exact graph. And that's all sine and cosine functions. Does that make sense? And something that I think is also pretty important to understand, and it's because of the co-function relationship, sine and cosine. If I go cosine of x, okay, and I put on top of it sine of x, okay, how far, let's just look at the maximums of these two curves that we're seeing here. How far to the left could I move this C point so it becomes the same as that A point? Pi over 2. So I'm going to take sine of x, and I'm going to move it pi over 2 to the left. So it should be plus, right? And it becomes the cosine, right? Does that make sense? Or you can do this. You can take the cosine and you can move it to the right pi over 2, right? And it becomes the sine. Okay? Now you might remember from other, now we can do some stuff with manipulating the order of the pi over 2 and the x. You guys remember that if I give you the sine of 30, that is identical to the cosine of what? Think about a right triangle. If I give you the sine of 30 degrees in a right triangle, is that equivalent to something from the other angle?
Yes.
Be the cosine of the 60 degrees, right? Does that make sense? If you type in sine of 30, you get 1/2. Type in cosine of 60, you get 1/2, right? So sine of 30 and sine of sine of 30 and cosine of 60 are the same. Those are complementary angles, right? Now we'll mess around with this later with how we can get this pi over 2 minus x instead of x minus pi over 2. But that relationship, these are showing complement. That pi over 2 is 90 degrees, right? Okay, so it's showing a complementary aspect with those graphs. So that allows us to then say that any graph that I give you, any sine graph that I give you, I can actually rewrite it in terms of cosine. Or any cosine graph that I give you, we can actually rewrite it in terms of sine. Does that make sense? Okay, so that's something to think about. Here's just a quick question. Can we, if I graph that purple one and then regraph cosine of, let's go pi over 2 minus x, does that give me the same graph? Okay, why? Can I do this? Can I take cosine of x minus pi over 2? Can I rewrite that as cosine of, let's go negative x. Let's do it this way. Factor out a negative, okay? And so if I factor out a negative, this is going to become negative x plus pi over 2. Does that make sense? Okay. Because if I distribute that negative through, it becomes positive x. And distribute that negative through, it becomes minus pi over 2. So this thing here, this f of x, and this are the same thing right now, correct? You guys remember the rule that said cosine of, like, negative theta is equal to the cosine of theta? Remember that? Yeah. Well, this negative right here is that negative. So I really don't need it because of the even odd properties of cosine. So it gives me then negative x plus pi over 2. Well, can I rewrite that as cosine of pi over 2 minus x? That make sense? And the reason I want to do that, because that then is the same thing as the sine of x. If we graph the sine of x on top, they become the same. And now you can see that if sine, give me a number for x. 7, so sine of 7 degrees is the same thing as 90 minus 7 degrees, or 80, cosine of 83 degrees. Does that make sense? So the complementary idea there is kind of expressed with that algebra, or seen with that algebra. But that, guys, that's the kind of nuts and bolts of how you are going to graph these functions. Okay. Tomorrow we might do one more. Okay. But there will be a couple of these, at least the bare minimum on your test on Friday. I will ask you, like, I will write an equation out, and I will ask you, okay, what does this 2 do? What does this 4 do? What does this pi do? Okay? And you'll have to tell me the transformation. Remember doing that in college algebra? If I gave you, like, y equals negative 2 f of x plus 3 minus 5. And I ask you, what's the negative 2 do? What's that plus 3 do? What's that minus 5 do, right? It'll be the same thing with sine, cosine, tangent. It might ask you to graph a couple of them. But tomorrow, introduce tangent. Hopefully get to Because of the tangent, probably work with the cotangent a little bit. The secant and cosecant, they are pretty easy to generate if we know what sine and cosine look like. Okay, so that's the plan for tomorrow. What we don't get through tomorrow, we'll finish on Wednesday and then introduce the inverse functions and how to graph those. We kind of already did that in Chapter 5 a little bit. Wrap everything up on Thursday, and then we'll test on Friday. And I will get you a practice test out. Hopefully by tomorrow. Yeah, I'll work on it. I've got one. I just want to kind of refine it a little bit, and I'll get that out to you.
Yeah. For my schedule.
Yeah.
But should I take? I don't know what to take. I was talking to that.
What are you going to do? What are your aspirations after high school?